Hello, today I am teaching you how to use equation and solve a problem related to DC motor. First, we will start with the DC shunt motor. The first equation is the terminal voltage, followed by the field winding current, and finally the line current. For the separately excited DC motor, the equations for terminal voltage, VT, and field current, IF remain the same as in the DC shunt motor. The difference lies in the equation for the line current, IL. The key differences between a DC shunt motor and a separately excited DC motor are the equations for line current and electrical power loss. These two equations are typically used when solving power flow problems. Here are the equations needed. First is equation to find EA. EA equals electrical output. K flux equals flux. Wm equals speed in radian per second. Next is the equation to find torque induced. T-IND equals torque induced. K flux equals flux. IA equals armature current. Next is the equation for VT. VT equals terminal voltage. EA is from previous equation. IA equals armature current. RA equals armature resistance. Next is the equation for IF. IF equals field current. VT is from previous equation. RF equals field resistance. RADJ equals adjustment resistance. Now moving on to question, this is a standard form of question. In this question, a table or a graph will be given. It is used to find new EA. From this question, the data given is this. This question asks to calculate the speed and torque during full load and speed during no load. The first step to answer this question is to find the no-load condition values, where IA equals 0. 1. To find speed, use this equation. In this question, EA and K flux need to be calculated. To find EA no load, we use this equation. Since IA equals 0, EA equals VT. To find K flux, we use this equation. To find EA for this equation, we will be using the graph. Wm no load is given. To convert RPM to radian per second, we use this equation. To convert radian per second back to RPM, we use this. Next, we need to find EA from the table. The EA from the table can be only used to find K flux. From the table, we need IF to find EA. The equation for IF is this. In this table, the value for EA is 240 because the IF is 0.96. The value for K flux is EA from table divided by no load speed. That will be 1.91. Now we got the value for EA and K flux. The value for no load speed is 125.65 radians per second. Now, we have answered the first part of the question. To find the no load speed, we need to determine EA and K flux. To find EA, we use the given equation. To find K flux, we first need IF, which allows us to find EA from the graph. Once EA is obtained, we use it to calculate K flux. To find the full load speed, we still use the same equation. Since the question states that there is compensating winding, this means there is no armature reaction. Therefore, the K flux remains the same as in the no load condition. To find EA at full load, IA, have values so it will not be the same as no load condition. Now we have obtained EA and K flux. The value of no load speed, also known as rated speed, is 115.7 radian per second. To find torque, we use this equation. P out is given, W rated is the full load speed. The torque value is 172.6 Newton-meter. Now we have answered the question. The speed at no load is 125.65 radian per second. Rated speed is 115.7 radian per second. Lastly, the torque is 172.6 Newton-meter. Now, here is another question. If IA is not given, we need to use the power flow equations to determine IA. The question will provide power losses, which will be used in the power flow calculation. Here is the given data. The first step is to calculate the no-load condition, just as in the previous step. The calculations remain the same. The full load condition calculation is the same as before, with the addition of power equation. From the power equation we can determine IA. This power equation consists of power in equals power out plus electric losses plus mechanical losses plus core losses. Usually the question will provide the value for mechanical losses and core losses. The full equation will be like this. From this point, we use simultaneous equations to solve for IA. This will yield two possible values for IA. We select the lower value because a lower IA results in lower losses. Once obtain IA, continue the full load step. The motor speed is 114.9 radians per second. Next, when the question states that there is no compensating winding, it means that armature reaction occurs, causing a change in the value of K flux. The problem remains the same as before, but with additional data. Number of turns. Armature reaction effect. These factors influence the flux, requiring adjustments in calculations. To find the full load speed, we use the same formula. The calculation for EA, full load, follows the same steps as in the previous question. However, since armature reaction affects the flux, we must first calculate the new K flux before determining the speed. To calculate the new K flux, we first need to find EA new from the graph. To do this, we use the IF equation to determine the new field current, which then helps us find EA new from the graph. Since IF is equals 0.6 ampere, the EA value from the graph is 185 volt. Once we obtain EA new, we can use it to calculate the new K flux. The value of K flux new is 1.47. Then we can find the speed, that is 149.29 radian per second. In this video, we covered the following key points. 1. General equations applicable to all problems. 2. Speed conversion formulas between RPM and radian per second. 3. Calculation flow for no-load speed determination. 4. Calculation flow for full load speed using the power flow equation. 5. Calculation adjustments when armature reaction is present. This structured approach ensures a clear understanding of DC motor speed analysis under different conditions. Hope this video helped you. Thank you for watching.